All right, there we go.
Okay, so where's it going to go? Well, this is good. Now you're not recorded as not knowing what the answer to that question was. It's going to go away because it's a positive charge, so my electric field is always pointing away. Always pointing away, so I get to this point, it's going to point away from it.
Okay. So we'll call that E1.
Let's do E2. Where's the electric field going to go relative to this -2q charge? Towards it. Because electric fields are pessimists, so they always go towards the negative.
Okay, so we're going to go towards. That's my E2.
And how about E3? Where's E3 going to go? Away. So if I'm going away, then I'm going kind of up at this angle.
That's my E3.
Yeah. So I've identified where all the charges, where all the fields are going. I have one that's going entirely in the x direction, so that one's probably pretty easy to figure out. It's not acting at an angle, so I don't have to break it into x and y directions. It's only going in one direction, so I can write that one down. Let's go ahead and solve for that one.
So E2 is going to be K times the magnitude of the charge. How big is the charge that's creating that field? It's 2Q. Why am I not plugging in the negative?
Don't plug in the signs of the charges. Where do I get the sign of the electric field? By looking at the physics, looking at the pictures, okay, the direction. And then I want to divide that
By the separation.
So how far is it from -2q to that diamond?
X. And I want to square that. Now, what direction is it going? Negative direction, negative I hat. That's my E2.
Done. Now can I just add E1 and E3 to that, as I currently have them? No, why not? They're not solely in the x direction, right? They're going in the x and y direction. So I need to break it into what shape? A right triangle.
So I got to draw right triangles into here. Pain in my butt. So I break it into the little piece of E3 going in the x direction and a little piece going in the y direction. And I do the same thing with my other triangle. Little piece going in the x, little piece going in the y.
Yes. Say it again. Yeah. Well, so no, you should write this so that it stays consistent once we start writing these ones out too. So you need to make sure that either negative I hat, or you could have the I negative out front, wherever you want that. But you need to make sure that you know that this is going in the negative direction. Okay. Now I look at these, and I see something that makes my life a little easier. E1 and E3. They're both created by a charge that's Q, and they're both the same distance away. How far away are they? Well, it's y to get up here, x to get over here. This is the total distance. How do I get that total distance? Pythagorean theorem.
So this total distance, we'll call it R, is the square root of x squared plus y squared. Comes from Pythagorean theorem.
All right, my triangle, x side, y side, hypotenuse. So same, K is the same, Q is the same, separation is the same. What do I know about the magnitude of E1 and E3? They have the same K, same Q, same R. They're the same. So the magnitude of E1 and the magnitude of E3 are the same. So what do I know about the magnitude of E1y and E3y? They're the same and they cancel each other out because they're going opposite directions. So do I have to solve anything in the y direction? No, screw the y direction. What about the x direction? What do I do about those? They're equal, going the same direction, so I can solve one of them and just double it, can't I? Okay. To solve one of those, what do I need to do? What kind of shape do I have to draw? I have to draw a triangle. I've got my triangle. I need to find the x piece of that triangle. I know I can find the hypotenuse. What else do I need? I need an angle. I need that angle right there. So let's see, what is that angle?
There's my theta. Turns out that theta is the same as this theta.
So I can look at that green triangle that we have up there,
And I can start solving some things. I can first write down what is E3. E3 is K times Q divided by x squared plus y squared.
How did I get that? E3 is K times the magnitude of the charge that's making it is this charge right here, divided by the separation squared. R squared is square root of x squared plus y squared squared is the x squared plus y squared. Yep. But I don't want E3, I want just the x component of that.
I need that E3 to get that x component, because if I look at this triangle, I can see cosine of theta equals the adjacent side, which is E3x over E3.
You see that in my triangle? Big one way up here. There's my triangle. I know the hypotenuse E3. There. Cosine of the angle. There's the angle. The adjacent side is the E3 in the x direction. E3 in the x divided by E3, the hypotenuse. This is a basic trick. Multiply your E3 to the other side.
And you get E3 times cosine of theta equals E3 in the x direction. So I'm almost there.
I now need to write what cosine theta is.
Cosine of theta.
The green theta I have is the same as the white theta. What is the cosine of this angle? What's the adjacent side here? X, what's the hypotenuse? Square root of x squared plus y squared.
So now we've got cosine of theta is equal to x over the square root of x squared plus y squared. So my E3x is equal to E3 times x over the square root of x squared plus y squared. And I can plug in that E3 so that E3x is equal to k times q over x squared plus y squared times x over the square root of x squared plus y squared.
Now, is this as simplified as I need to get it? Do I have to keep solving for other variables? I couldn't just leave this theta in here. To get my answer, I have to put it in terms of things that I know.
The things that I know, if I go up to the very, very top, the very first thing we found, I need it in terms of q,
negative 2q, x, and y. So those are the variables. I can assume that these variables that we were given, I can treat those like they're numbers. So as long as everything is written in terms of one or more of these variables, I've simplified it enough. I've solved the problem. So let's look
E3x.
I've got a K. K is universal constant. We're good there. Q, that was one of the charges we were given. I've got X's and I've got Y's. So these are all things that I was given. These are all things that I knew. Okay?
So I don't have to keep simplifying stuff. I just have to write the total electric field. I'm going to write it down, and we're going to see if we can reason out where all this crap comes from. Okay.
What the heck? I explained a gigantic leap. Not really, kind of little hop. How did I make this happen? Where did the 2 come from? I doubled E3x. Why did I do that? Because there's 2 of them, right? And what direction are they going? They're going to the right, so they're the positive I direction. So that stays positive. Where did this come from? That's E2. 2 to J2 Q K over X squared, and everything's going in the I direction. Negative because of the negative. So there's my total electric field. That's our total answer. On an exam, typical point value for this, a full, difficult, challenging problem I consider worth 20 points. I will consider this one to be worth 10. Okay? So that you have an idea of difficulty levels. That is a 10-point problem. Okay? You can't see this on YouTube, but they're crying a little bit. A few of them died a little on the inside. We'll say that again and we'll actually record it. So this is example 9 in the book. I use Gauss's law to find the electric field of a very large uniform sheet of charge with sigma coulombs per square meter. So I have this sheet, big sheet of charge. Do you want it to be positive or negative? Let's do positive. And I'm told to use Gauss's law to find what is the electric field of this sheet. So what's the first thing I should write? If I'm told to use Gauss's law, what makes sense to write down? Gauss's law. And what is Gauss's law? Integral of E dot dA equals Q inside over epsilon naught. Now for Gauss's law, what they need for you to do is draw something called a Gaussian surface. And this Gaussian surface is going to enclose some charge. It's going to represent the charges that are on your little sheet. What they do in the book, what's typically done with this kind of problem is you choose a cylinder to be your Gaussian surface. So I'm drawing a little cylinder. Let's see. Okay, so there's my cylinder. I drew it, wonderful. And what I'm representing with this Q inside is the charges that are inside of this cylinder. Charges that are inside that little circle that's actually on the plane, however many there are. Did I specify how big that cylinder has to be? I drew it, but did I say the cylinder can only be this big? There's no limits on how large that can be. So this could be an infinite cylinder, which means it can represent the whole infinite plane. So this is a rough representation. Okay. So now we got to write down the left side and we have to write down the right side. I have a shape. I have an electric field. Where's the electric field going? Going out. So if I'm above this plane, it's going up because it's always going away. If I'm below this plane, it's going down, always going away. So I can see that I have 3 potential surfaces for this cylinder. For a cylinder, I have 3 different surfaces. Here's my cylinder. I have the top surface that the electric field's going up through. Got the bottom surface that I'm going down through. And then I have the cylinder wall. Do I have electric field going through the cylinder wall? My electric field's going up. The cylinder wall is kind of parallel to the electric field. So my field lines aren't going through the wall. Because they're not going through the wall, E dot dA, that dot means something. That's the dot product. That means that if your wall is going the same direction as your field, it's 0. So there's no field lines going through this wall. All my fields are going through the end caps. So I only have 2 fields. I have a field going through the top end cap and the bottom end cap. Top. Bottom. Q in over epsilon naught. Okay, I have a surface. I've got an E, so I'm going to get E out. It's going through the circle that is a plane. What is E dot dA for going up through a plane? What's that? EA? Through a plane on one side is EA. Yeah. So I've got the top one is E times A. How about the bottom surface? That's electric field going through a single plane. It's going through the bottom surface, so that's E times A. Q in. What kind of surface is this? Is this a line? Is this an area? Or is this a volume? It's plane. So that's X and Y directions. What's that? Surface. So it's an area. So which charge do I plug in? Do I plug in Q equals lambda L, Q equals sigma A, Q equals rho V? Sigma A. So Q in is sigma A over epsilon naught. What's EA plus EA? 2EA equals sigma A over epsilon naught. I can cancel out my A's. I can divide by 2. And I got my final answer. E equals sigma over 2 epsilon naught. I could have done a shortcut, right? I've got this plane, I'm going through both sides of the plane, so instead of doing the top and the bottom separately, I could have used a plane on both sides. I could have just gone straight to 2EA. Either way, you get the same answer. E equals sigma over 2 epsilon naught. So that's how you use Gauss's law. Steps, write down Gauss's law, figure out what's on the left side and what's on the right side. The left side is always going to be E times whatever surface area you have. The right side is going to be whatever charge is enclosed divided by epsilon naught. The charges that are enclosed are often going to be one of these 3. That is the easiest version of Gauss's law that you'll get. Sometimes you'll have to integrate over the charges. Sometimes the charge will depend on position. This isn't one in the homework. This is example 9 from the textbook. This was one that somebody posted to the discussion board like 6 hours ago about how to do. They specifically asked for this one. Yes, please. In reality, yes. In the problems that you're going to solve in here, no. Gauss's law works because of symmetry. Lots of arguments about how things are going, things being symmetric. It gets really complicated when you break symmetry, so I'm not going to break symmetry. You can assume. You're getting the easiest level of Gauss's law that I can do. Any other questions? Where does this crap apply? Why do you have to know this? Who cares? I'm gonna be a doctor. I don't need to know any of this shit. It is useless for me. Ever had an MRI? Yeah, you're being sent into a big, gigantic magnetic field that has electric fields going along with it. You need to be able to calculate the electric fields that are acting on the body of your patient. If you cannot do that, if you don't know how that works, well, you'll be fine because other people have worked it out, but you could kill your patient. So this physics goes into the MRI, making sure you don't kill yourself. It gets a little deeper than that, but yeah, this is all useful. It's just other people have done the back end work.